Hi everyone, this is Professor Oaks, and in this video we are going to discuss polynomial functions and their graphs. So here's a summary of some of the polynomial functions that we've studied so far: the zero function, constant function, linear function, and quadratic function. And I mentioned before that we could extend this to degree n and just make sure that the highest degree term does not have a coefficient that is 0. So these an minus 1, a1, a0 are all the coefficients of the polynomial. A0 is the constant coefficient or the constant term. The an is the coefficient of the highest power or the leading coefficient. And an x to the n is the leading term. So let's do some examples of identifying these different items in each of these polynomial functions here. If I look at the first one here, I look for the highest power, and that will be the degree, so that will be 8. The constant term is, well, that is 0 because there is no term without any variables in here, and the leading coefficient will be a 1 because that's the coefficient of the highest power term, and the leading term is x to the 8th. Let's try again. This here is a constant function, so the degree is 0, the constant term is 5, the leading coefficient, well, this is actually a tricky one because it's 1 and the leading term is 5 because there's only one term here, the constant term. All right, so here f of x is x minus 3 times x plus 2. So this is a polynomial, and you can recognize it better by distributing x squared plus 2x minus 3, x minus 6, or x squared minus x minus 6. The degree is the highest power, 2, constant term, negative 6, leading coefficient 1, leading term x squared. Let's try again. So polynomial functions, degree, highest power 3, constant term is 0 because there are no constants here. Leading coefficient, that will be the 1/2, leading term 1/2 x to the 3rd. Same thing here, we look for the degree, 2, constant term 0, leading coefficient square root of 3, and then the leading term is square root of 3 x squared. So now that we have this a little bit settled here, let's try to explain why each of the following is not a polynomial. All right, so this actually is a function g of x, x squared plus 3 over x minus 1. This is a rational function, so it is not a polynomial function. Here we have g of x is 3x minus 4x to the negative 1. That's 3x minus 4 over x. Here we see we have a rational function here again. And that was easier to recognize when I wrote this with the x to the negative 1 power being 1 over x. Here, this is also a rational function, so it is not a polynomial. And here, we have a square root function, so square root functions are not polynomials. And that's it. All right, so that's the basics of different polynomial functions here. So now let's look into the graph of polynomial functions. So you can see some examples that polynomial functions will be smooth, continuous curves for their graphs, and here's some example of a graph that cannot be the graph of a polynomial function. A power function is just a function of the form ax to the n, and if you recognize what we were doing here, that's why we were picking out all of the leading terms, because the leading terms are power functions. All right, so all power functions are monomials or one-term polynomials. So the end behavior of polynomials here, power functions fall into two categories according to whether n is an even or odd positive integer. So here we go. If the p of x has an odd degree, then if the leading coefficient is positive, this is what the graph will look like for its end behavior, something like x to the third, x to the fifth, x to the seventh, etc. But the leading coefficient is negative. Here's what the end behavior will look like, something like negative x to the third, negative x to the fifth, negative x to the seventh, etc. If p has an even degree and the leading coefficient is positive, this is what the end behavior will look like, something like x squared, x to the fourth, x to the sixth, etc. And if the leading coefficient is negative, this is what the end behavior will look like, something like negative x squared, negative x to the fourth, negative x to the sixth, etc. So let's determine the end behavior of each polynomial and then use the transformations of y equals x to the fourth or y equals x to the fifth to sketch the graph of the function. All right, so I know that y equals x to the fourth looks like this, and y equals x to the fifth looks like this. So I know what the end behavior looks like. All right, like this, like this, like this, and like this. All right, so hopefully that's dark enough there that you can see this now. So now f of x equals x plus 3 to the fifth. That means a shift 3 units to the left. So I know that I have 1, 2, 3 units to the left, and this is what the graph will look like. All right. And if I wanted to write out the end behavior formally, I would just use the information that's on the sheet here, right? So the end behavior for x to the fifth would be right here as x goes to negative infinity, or y goes to let's see, what do you want to go? Y goes to negative infinity as x goes to negative infinity, and you see also up here as y goes to infinity as x goes to infinity. So again, right here is what you want to write, and right here is what you want to write if you're trying to describe the end behavior in words. Actually, I thought that was on the screen the whole time. Oh boy, what a time to be alive. All right, so now we have f of x is equal to x to the fifth plus 3. So this is a shift of f of x equals x to the fifth, 5 units up. So here we go. 1, 2, 3, 4. Oh, sorry, 3. 3 units up. I circled the 3. I wrote 5. There we go. What a time to be alive. And here we go. That is what this looks like. So the same end behavior as the function in problem A here. So y goes to negative infinity as x goes to negative infinity, and y goes to infinity as x goes to infinity, or y approaches infinity as x approaches infinity. All right, so now let's do another one here. This has a function of f of x equals x minus 1 to the 4th power minus 2. So it has a shift 1 unit to the right and a shift 2 units down. All right, so here we go. 1 unit to the right, 2 units down. I know what the end behavior is because it's the same as y equals x to the 4th. So here we go here. So this will look like this. Easy enough. So again, the end behavior for y to the 4th you can find right here on this sheet here. So y approaches infinity as x approaches negative infinity, or y approaches infinity as x approaches infinity. All right, so that would be the end behavior if I wrote it out using mathematical symbols like that. Now, let's use zeros to graph polynomials. I know that we've done things like this before, but here we are repeating for general polynomials of degree n, not just quadratics and cubic functions. All right. So if P is a polynomial and C is a real number, then the following are equivalent. C is a 0, P, x equals C is a solution of the equation P of x equals 0, x minus C is a factor P of x, and C is an x-intercept of the graph of P. So consider this function. P of x is 3x to the 4th minus 6x to the 3rd minus 11x squared plus 4x plus 6 equals x plus 1 times x minus 3 times 3x squared minus 2. What can be said about the real zeros of P of x? Well, if I set each of these factors equal to 0, I can find the real zeros of P of x. So one of them is negative 1, one of them is 3, and then, well, I can go ahead and add the 2 and then divide by 3 and take the square root. So x is equal to plus or minus the square root of 2 over 3. So one of the zeros is square root of 2 over 3, and one of them is negative square root of 2 over 3. So there are 4 real zeros here. So we can say that C equals negative 1, 3, square root of 3 over 2, or 2 over 3, and negative square root of 2 over 3 are zeros of P. And then we can say x equals negative 1, 3, square root of 2 over 3, and negative root 2 over 3 are solutions of P of x equals 0. And we can say x plus 1, x minus 3, and then x minus root 2 over 3, and x plus root 2 over 3 are factors of P of x. And we can say negative 1, 3, C equals negative 1, 3, root 2 over 3, and negative root 2 over 3 are x-intercepts of the graph of P of x. So all 4 of these things hold true for this function P of x. What a time to be alive. Now, the intermediate value theorem for polynomials. If P is a polynomial function and P of A and P and B have opposite signs, then there exists at least one value C between A and B for which P of C is equal to 0. So use the intermediate value property or intermediate value theorem for polynomials to show that f of x equals x to the fourth plus x to the third minus 9x squared minus 3x plus 18 has a real 0 in the interval from -2 to -1. Well, this is A and that's B, so we have, here's -2. All right, so f of -2 was less than 0, and here is -1. So f of -1 is greater than 0. So this number is less than 0, and this number is greater than 0. And this is actually a polynomial function that's continuous between -2 and -1. Then that means that somewhere in the middle, the function had to be negative if it was to go, negative, and then somewhere it had to be positive. Then, of course, it went through 0 somewhere in that interval. All right, so here is, since f of -2 and f of -1 differ in sign, all right, one was negative and one was positive, that means that f of x equals 0 somewhere between x equals -2 and x equals -1, or in the interval of -2 to -1. All right. So now here is a summary of graphing a polynomial function. So just remember to memorize all of these steps of graphing the polynomial function for the rest of your life, and it will be fine. All right, so now let's do an example of applying these steps that you've just memorized for the rest of your life there. So sketch the graph of f of x equals x to the fourth plus 6x to the third plus 4x squared minus 24x minus 32. So that is equal to x plus 2 squared times x minus 2 times x plus 4 using the steps above. So we're going to determine the end behavior of the graph of the function. Well, the leading term is x to the fourth. So the leading term is x to the fourth. So I know that the end behavior looks like this. All right, and actually, I am going to get my highlighter out so that you can see that a little bit better. Maybe I should just use highlighters all the time. What a time to be alive. In living color right here. It's only 3 colors, white, black, and yellow, but here we go. All right. Find the x and y intercepts of the graph of the function. So the x-intercepts, since this is in factored form, x plus 2 squared, x minus 2, x plus 4, are easy to find because we can just set each factor equal to 0 here. So x plus 2 equals 0, x plus 2 equals 0, x minus 2 equals 0, x plus 4 equals 0. So x could be -2, x could be -2, x equals 2, x equals -4. So we have x equals -2 twice. So we say that's multiplicity 2, x equals 2, and x equals -4. And the y-intercept Here we have f of 0 to find the y-intercept. So we have 0 to the 4th plus 6 times 0 to the 3rd plus 4 times 0 squared minus 24 times 0 minus 32. It's negative 32. So it's at 0, negative 32. So we have all of the intercepts today. All right. So now we have x equals negative 2, multiplicity 2, and x equals 2, x equals negative 4. This is multiplicity 1, multiplicity 1. If these numbers are odd, that means that, now I know we've talked about this before, but the graph of f will just cross the x-axis at those points, and if it's an even multiplicity, the graph will touch the x-axis. So these will cross the x-axis at those points, and here at those points, and here this one will cross the x-axis at the point, but this one will not cross, so it doesn't cross the x-axis at that point, or just, in other words, it just touches the x-axis but does not go past it. Now, think about that. All right, think about this, because here's an example of this. Because if we have x squared, see how that was even, and so this actually just touched the x-axis right here. If we have x to the 3rd, that's odd, and I hope that you can see if this was odd, then we crossed the x-axis. All right, so think about this. Just be careful about whether the function should actually touch or cross the axis at each of the x-intercepts, or at each of the zeros of the function. So determine the maximum number of turning points on the graph of the function, and that will always be n minus 1. So n was, again, 4. N equal 4, that's the degree of this polynomial function. All right, so the maximum number of turning points will be n minus 1, or 4 minus 1, so the maximum number of turning points is 3. Now we're going to determine the end behavior of the graph near each x-intercept. So remember that f of x was equal to x plus 2 squared, x minus 2, x plus 4. So the intercepts were negative 2, x equals 2, and x equals negative 4. So then for x equals negative 2, what we're actually going to do is we're going to substitute in the negative 2 for every factor that wouldn't become 0. So negative 2 plus 2 would be 0. So we have negative 2 is our x-intercept. So we have x plus 2 squared, negative 2 minus 2, negative 2 plus 4. And negative 2 minus 2 is negative 4, and negative 2 plus 4 is 2. So then we have negative 4 times 2 is 8. Negative 8 here. And so we know that negative 8x plus 2 squared is a parabola that opens downward. All right, I'm not going to get more accurate than that, but it's a parabola that opens downward. Now, for the x-intercept of 2, we have x plus 2 squared, x minus 2, x plus 4. I'm going to substitute that 2 into every factor that wouldn't become a 0. So 2 plus 2 squared, 2 minus 2 would be 0, and then 2 plus 4. So 2 plus 2 squared is 4 squared, which is 16, and 2 plus 4 is 6. And then 6 times 16 is 96, so 96x minus 2. And I know this is a line with a positive slope. All right, so a line with positive slope, so it will look something like this. I'm not going to say anything except that it's a line with positive slope, just like I said that this one is a parabola opening downward. Now, for the x plus 2 squared, x minus 2, x plus 4, if I substitute the negative 4, negative 2 plus, negative 4 plus 2 squared, negative 4 minus 2, x plus 4, we have negative 4 plus 2 squared, negative 2 squared, which is 4. Negative 4 minus 2 is negative 6. X plus 4. 4 times negative 6 is negative 24. So negative 24, x plus 4. And this is a line with a negative slope. So that will have something that looks like this. And now I'll use all the information in steps 1 through 5 to draw a complete graph of the function. All right, so I know, first of all, it had an x-intercept at negative 2, at negative 4, at 2, a y-intercept at 0, negative 32, so negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh boy. All right, so let's me get my ruler out here because I want to be as accurate as possible. All right, maybe I do, but I mean, if you don't want to be, then that's up to you. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, negative 20. Right, so negative 10, negative 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, negative 30, negative 31, negative 32. All right, now I know that the end behavior was like this because of the x to the fourth. And then at x equals negative 2, the graph touched the x-axis, but then this also was the behavior. So it's going to look like this. And then at x equals 2, that was, x equals 2, we had something that looked like a line, and it crosses the x-axis. So it looks like this. And at x equals negative 4, we had something that was a line with a negative slope that also crossed the x-axis. So then you just fill in the gaps in between. So again, this is just a sketch, but it has to go down and then turn around to connect and then go all the way down to negative 32 at some point, and then come back around and at some point and then connect with this part up here. All right, so that is a complete graph of the function. All right, something that has this general shape. And how many times did this turn around? A maximum of 3 times. So here's one point where it turned, a second point where it turned, and here's a third point where the graph turned. All right, so there you go. That is a complete sketch of the function here. Good enough for my purposes. All right, you might want to be a little bit more accurate on where this relative minimum is, but at this point, we haven't learned the techniques to do that except for plotting points, and I don't want to have you deal with all of that today. Maybe tomorrow. Maybe tomorrow will be the day for you to do that. All right, so let's sketch the graph of f of x equals x to the fifth plus 2x to the fourth minus 3x to the third equals x to the third times x minus 1 times x plus 3 using the steps above. So let's determine the end behavior of the graph of the function. So the leading term is x to the fifth, so n equal 5 is the degree. And then, since that is the case, the leading term is x to the fifth, so the end behavior will look something like this. All right here and here. So now let's find the x and y intercepts of the graph of the function. So the x-intercepts, we see that this is already factored for us. So we have x to the third, x minus 1, x plus 3. So x equals 0, x equals 0, x equals 0, x minus 1 equals 0, so x is 1, x plus 3 equals 0, so x is negative 3. So we have x equals 0 with multiplicity of 3, x equals 1, multiplicity 1, x equals negative 3 with multiplicity 1. And now for odd multiplicities, we know that this is odd. So this will mean that the graph will cross the x-axis at x equals 0 and also cross the x-axis at x equals 1 and at x equals negative 3. All right, and now we need the y-intercept. So f of 0 is 0 to the fifth plus 2 times 0 to the fourth minus 3 times 0 to the third. And hopefully you already realized that that was 0. So it's 0, 0. And then the maximum number of turning points will be n minus 1, which is 5 minus 1, or 4. So now, let's go ahead and determine the behavior of the graph near each x-intercept. So remember that the function was f of x is x to the third, x minus 1, x plus 3. So we have x equals 0, x equals 1, x equals negative 3. So near x equals 0, we have x to the third times 0 minus 1, 0 plus 3. So x to the third times negative 1 times 3, so negative 3, x to the third. And here we go. All right, because this is the general shape of negative x to the third. Near x equals 1, we have x to the third, so 1 to the third times x minus 1 times 1 plus 3, 1 times x minus 1 times 4, or 4 times x minus 1 is a line with a positive slope. So this will look like this. Remember, these are just sketches here. And then near x equals negative 3, we have negative 3 to the third, negative 3 minus 1, x plus 3. So negative 27 times negative 4, x plus 3. So negative 27 times 4, what is that going to be? That will be 108 times x plus 3. So that will be a line with a positive slope. So again, I'm just going to sketch a line with a positive slope. And now I'm ready to go ahead and draw a somewhat complete graph of the function, or a sketch of the function here. So let's go ahead and get our done, right? Get our done. All right, so what a time to be alive. So what are the points that we had? We had a a 0, 0. All right, an x-intercept of 0, a y-intercept also of 0, an x-intercept of 1, and an x-intercept of -3. And then I knew the end behavior looked like this. All right, and then near x equals 0, we crossed the x-axis, but it sort of looked like this. All right, and then near x equals 0, then near x equals 1, we have a behavior that's a line, but remember that should have also crossed the x-axis at x equals 1. And then at x equals -3, we had a line with the a positive slope here. Yeah, so it also crossed the x-axis at x equals -3. So then if I connect these so that it's a smooth curve, it comes up, so it must come down at some point. And don't worry about how high, because you haven't talked about how high yet. But there we go. The graph will look something like this. What a time to be alive. Again, this is just a sketch, so I haven't really taught you how to find the relative maximum and minimums here, except for using a computer yet, but we will get to that at some point. But hopefully you enjoyed this video here on polynomial functions and their graphs. And hopefully you are already looking forward to the next video. What a time to be alive. Have a great day, everyone.